Good afternoon. So we'll begin with module 3 right away. Start with implicit differentiation. And from the word itself, it's the opposite of explicit. And let me explain the difference between the two kinds of differentiation with this example. Let's find the derivative of y with respect to x if x and y are related by this equation. Now note that here y is not given explicitly in terms of x. So one way we can find y prime or the derivative of y with respect to x is to first solve for y in terms of x. That can be done. No, not always, but in this instance, we can easily get y in terms of x. So let's solve for y. And we can do that by factoring out y, giving us this equation. And we can get y by simply bringing this down. So we have y equals 1 all over x squared plus 1, which we can rewrite as x squared plus 1 to the negative 1, so that we can easily get its derivative by applying the chain rule for power functions. So getting y prime, we apply the power rule, bring down, subtract 1, differentiate the base. So we get this. And simplification gives us the derivative as negative of 2x all over x squared plus 1 quantity squared. So here we have gotten the derivative by explicit solving for y first, then differentiating after. However, there's another way of getting the derivative of y without resorting to solving for y first, especially if that cannot be done, as in many cases. But let me show by implicit differentiation how to get y prime. We start by directly differentiating the given relation or equation between x and y. So it's the given equation here, and we differentiate both left hand and right hand sides with respect to the independent variable, which in this case is x. So if we do that, we can apply the usual rules of differentiation. So for instance, for the left hand side, we can apply the sum rule. We can differentiate term by term. And then for the right hand side, the constant function rule, which states that the derivative of any constant is 0, giving us the following. Okay, derivative of the first term plus derivative of the second term equals 0. Now for the first term here, we can apply the product rule. If we do that, we'll get the following. It's the first function, x squared, times the derivative of the second function with respect to x, so that's just y prime, plus the second function, which is y, times the derivative of the first. So the derivative of x squared is 2x. And then we just change notation here from dy dx to y prime for a shorter hand notation. And then this gives us an equation relating y prime, x, and y. And we can solve for y prime here. And we can do that by isolating or transposing terms without y prime to the other side. So we will be transposing this one, giving us this equation, which we can solve for y prime by factoring out y prime, then dividing by the factor here. So giving us y prime equals negative 2xy all over x squared plus 1. Now, note that this is already a derivative of y with respect to x, only that it is implicit in x and y, meaning the derivative, instead of being given directly in terms of x alone, the independent variable, the derivative now is in terms of both variables, x and y. So that if we know the values of x and y, we can substitute those values into the formula here to get the derivative there. However, we can show that the two answers are just the same by using this again, this one here. We can plug this expression for y in here to get this one. So replacing y by this, and then simplifying, we get the following: negative 2x all over x squared plus 1 squared, which is just the same as the previous answer. Okay? Now, as I have said, we cannot always do method 1. Only in actually the very simplest of equations can we do that. So usually we resort to implicit differentiation to get y prime, and that would be in terms of both x and y. So we call it implicit differentiation since the derivative is given in terms implicitly in terms of x and or y. Let's show that with another example here. So find y prime given the relation here between x and y. By the way, I call it relation since y is not necessarily a function now of x. If we try to sketch the graph of this equation, which I haven't shown here, actually by the vertical line test, it will fail to be a function. So we call this really a relation, or just an equation relating x and y. But still, we can get the derivative by implicit differentiation as follows. Now, what you do is simply apply the rules again, term by term differentiation. So let's start with the first term here. Applying the product rule again, first times derivative of the second, which is 2x, plus the second, which is x squared, times the derivative of the first, which is 3y squared. Don't forget y prime, and this is where students often get confused. You're differentiating y cubed, not x cubed with respect to x, so you have to apply the chain rule. In other words, after applying the basic rule, which is the power rule in this case, where you bring down 3 and subtract 1, you have to differentiate the base, remember, with respect to x. That is dy over dx, which is just y prime. So to omit y prime would give you a wrong equation here for the implicit differentiation. One wrong thing like that would cost you almost the whole problem. So that's the first term. Then we do also for the second term, we differentiate it, applying the chain rule, remember, for trigonometric functions. So constant, so that's just 2 times the derivative of sine y. How do you differentiate sine y? We know that the derivative of sine y is cosine y. And then since this is not x, but rather y, we have to multiply always by the derivative of y with respect to x. To omit y prime again would mean a wrong solution, and thus a wrong final answer afterwards. And then right hand side now, we differentiate with respect to x. So we need the product rule again. So first times the derivative of ln y, we know this to be y prime over y. Actually, we have stated it as a formula. The derivative of an ln can be obtained by getting the reciprocal, remember, of the expression inside multiplied by the derivative of the one inside. And then second term, which is ln y times the derivative of the first with respect to x, and that is just 1, written here for the purpose of showing you what happened. So this gives us an equation allowing us to solve for y prime implicitly in terms of x and y. Now, how can we solve for y prime here? Well, first, we need to manipulate this equation so that no fractions appear. And then second, we must isolate y prime on one side. And to be able to do that, we have to transpose all terms containing y prime on just one side of the equation. But first, let me simplify this equation by multiplying by the LCD, which is y here, the only term, okay, in the denominator or in a denominator. So we multiply both sides by y first so that no fractions appear. So we have to do it term by term. So here we multiply by y, that becomes y to the fourth. Y squared becomes y cubed. And then here you have 2 times y. And then here y cancels out. So just x y prime. And then a y here. So no fractions appear in this line. And then collect all with y prime on one side. We have this equation. Of course, all other terms will be on the other side. Those without y prime. Then here, those with y prime. And the reason for doing so is that we can isolate y prime by factorization of y prime, which I will just show here. Although you can omit this step once you're familiar with the process. Factoring y prime will leave you with just the coefficients, okay, quote unquote, coefficients of y prime. And afterwards, you can just bring it down to get the expression for y prime. And we have y prime in terms of x and y, found by implicit differentiation. So that's implicit differentiation in a gist, but I plan to move ahead with the other topics. At least you have an idea of how to go about the process of differentiating implicitly. And don't worry, we will have exercises afterwards once we are through with all the topics. But at least you understand now how to get the derivative implicitly. So it's just practice that will make perfect for your understanding of differentiation. Any questions so far? So it's just all the rules you've learned in the previous module, except that you're now dealing with an equation instead of a function. So we apply this to getting the equations of lines tangent to curves. And when you say curves, they need not obey or what they call this, they need not satisfy the vertical line test. So you can have closed curves here, like circles, ellipses, and other shapes, as we shall see in this example here. So suppose you encounter a question like this where you're given, you see here, an equation, a relation, and it has a graph, but you don't have an idea of the graph. Don't worry, you don't need really the graph to solve this one, but I'll show you the graph anyway later on. And you are being asked to find tangent lines to certain points on the graph. Okay, I have omitted the additional question here where you should find the equations of the lines tangent to the graph of this equation at x equals 1. Just take note of that, at x equals 1. So you're not given the points of tangency yet directly. So the first thing you need to do or need to find are the points of tangency. So again, at x equals 1, that means you substitute x equals 1 so that you can get the corresponding y coordinates. Of course, if it's the y that's given, you have to solve for x. So if we substitute x equals 1 into the equation here, replacing each occurrence of x by 1, we get this. And this gives you an equation in y. And I won't be detailing out the process of solving for y here. It's your algebra, it's your math or high school math. So you are presumed to be familiar with the process of solving a quadratic equation by factoring and by the quadratic formula. So that's quadratic, it's factorable, and you can quickly solve for y or easily solve for y. So in other words, once you substitute x equals 1, you'll be able to get the corresponding y coordinates. And that means there are 2 points in consideration since there are 2 values for y. So the 2 points of tangency are 1, -2, and 1, 3. And we are required to find the tangent lines at those points on the graph. So to be able to do so, we need the slopes of the tangent lines. And as discussed in a previous module, module 1, the slope is simply the derivative. In other words, we will be finding the derivative of y, and this time implicitly. So step 2, find the slopes of the tangent lines. First, find the derivative implicitly. Let me just explain how this was arrived at. So we differentiate term by term. So differentiating x squared, that's 2x with respect to x. Differentiating y squared with respect to x, chain rule, 2y. Don't forget the y prime. And then here I applied the product rule. I thought of the first term as negative x and y as the second term. So it's negative x times the derivative of y, which is y prime, and then plus y times the derivative of negative x, which is -1, so you have negative y. Anyway, you can verify that. The common error students make in differentiating terms containing negative is in the failure to distribute the negative sign. So actually both have to be negative, but the tendency is to have one of them positive. But anyway, verify this is the correct differentiation. And of course, derivative of the 0 constant there is 0. Okay, we did not just copy the 0, we differentiated the 0, although the derivative of 0, since it's a constant, is also 0. If this were a 1 or a 2 or any other number, it would have been also a 0 here. Now we can solve for y prime the usual way and just verify that if you collect y prime on one side, factor out, divide, you'll be getting this expression for y prime. Now, once you have the derivative, it would now be easy to get the slope since you have the values of x and y. You have both x and y coordinates. So you just consider one at a time, get the slope. So for example, for the point 1, -2, we just plug in x equals 1 and y equals -2 into the expression here, we get the slope. So I've shown here the substitution and the final value, 4/5. In other words, the slope of the tangent at this point of this curve is 4/5, found by implicit differentiation first. And we do it for the other points, if there are any. So let's do it for 1, 3. We plug in 1 and 3, x equals 1, y equals 3. Simplify, we get 1/5 for the slope of the tangent at this point. Now, that means you have everything you need to get the equation of the tangent lines. They are just lines, so you just need a point and a slope, or the slope. So we use the point slope form to derive the equations. For step 3, we find the equations now of the tangent lines. So let's consider the point 1, -2, whose slope we already know. I mean, the slope of the tangent to the curve at this point. So we just use what we know from algebra. Point slope form, remember, y minus y sub 1 equals m times x minus x sub 1. So y minus -2, so you have a y plus 2. And then here, x minus 1. and then times m. And then we just simplify in the form y equals mx plus p. And we do it for the other point. So we know now that the slope of the tangent there is 1/5 at the point 1, 3. We do the same. And without having to discuss the details, we get this as the equation of the tangent line to the curve at this point. Now, just for the purposes of showing you why our answers are correct, I have used GeoGebra. You can download it on your in your cell phones. I'm not sure how to do it with your computers. And you can type in just the equation of the curve. You can type that directly into GeoGebra, and also the equations of the tangent lines, and you'll see that they are indeed tangent lines to the curve at the given points. So here's the curve, here's the equation. It's an ellipse actually that is rotated, I think 45 degrees counterclockwise. Anyway, that's not important. You won't be required to graph such curves anyway. And here are the tangent lines, the equations we have found. I plotted them, and we see that they are indeed tangent to the curve. And in fact, it's not hard to see that we have the points of tangency there. For instance, this is 1, 3, and this is 1, -2. Okay? And without, of course, showing you the graph, we can still get, I've just shown you that you can still get the equation of the tangent lines algebraically, or rather using the methods of calculus. Is there any question? So let me leave that topic, since all that's needed is practice. Now let's go to derivatives of inverse trigonometric functions. Now, so far what I know is that all you are required is know how to find the derivatives of inverse trigonometric functions and nothing else. In other words, it's just like what you did in the previous module, where you are given the